Today is going to be a whirlwind of a lecture. It's going to get pretty interesting. So let's get into it. Suppose this is your surface M. We'll go ahead and pick a point P at the very top. It's easier just to draw the tangent plane there, but that could be any point P on the surface. And we define this shape operator thing, right? The shape operator at the point P sends an element of the tangent plane into itself. This is your tangent plane. And the definition is just the negative covariant derivative of u. And what's u? U is this unit normal vector everywhere. Okay, so that's u. And of course, it's defined up here as well. And then you look at the rate of change of u in some tangent direction v. Typically, you might let v be a unit vector, but it doesn't have to be. And that's, when you see what the rate of change of u is in any given direction, it tells you how the tangent plane is curving, which tells you how the surface is curving. Okay, so this shape operator is pretty well named. By the way, let me comment that outside of this class, the shape operator is called the second fundamental form. The second fundamental form. So if you're reading advanced papers and stuff, and the dot product is called the metric, or the first fundamental form, and the shape operator is called the second fundamental form.
Is there a third?
No, well, not that I am aware of, but it's a good idea. We should come up with the third.
I'll get on that.
Okay. So here's an interesting lemma. Okay. And that is that if you have any curve on the surface going through the point P, let's call that curve alpha of t. And you could even think of v here as alpha prime of t, right? So the velocity vector of a curve, that's what tangent vectors are. Then we have an identity, and this identity is that alpha double prime of t dot product u let's go ahead and evaluate this at p, where p is equal to alpha of 0. This is equal to the shape operator at the point P of alpha prime of 0, dot product alpha prime of 0. Okay. I left out the zeros. It's just because we're doing everything at the point P, okay? So just realize that this is all at t equal to 0, okay? At the point P there. Okay, now how do you prove this? Proof. So basically one line. 0 is equal to, leave a gap here if you're taking notes, alpha prime of t dot u. Okay, you agree? Because see, alpha prime is a tangent vector. U is a normal vector, right? And both, by the way, this is of course u evaluated at alpha of 0. So if I want to write this out fully, right, this is alpha prime of t dot product u of alpha of t, okay? So this is what is implied there, okay? Because where else, of course I want to be doing all the computations at the same point, right? Okay, but it's also good to write things out. And then what we're going to do is, so by the way, this is a function, it's a number at each point, right? Dot product of two vectors is a number. It's a function of t, right? So this is a function of t, if you like. But it's also defined along the curve, right? And so then we can take ddt of this or we can, here's the interesting thing. I'm going to take ddt of it, or I can apply alpha prime to this. Okay, I'm going to take the directional derivative of it. And I'll go ahead and write like this. I think that's what the book does. But it's also the same thing as taking ddt of this. Okay, so there's a kind of, we proved that you could do this several lectures ago. But so this is ddt. So on the one hand, this is going to be alpha double prime of t. Okay, so when I'm doing the product rule, dot product u plus alpha prime of t dot product, and then I can take this covariant derivative. Okay, I'm really taking ddt of both sides, right? If you take ddt of this, you get that. If you take ddt of this, well, you're taking the derivative. It's by the chain rule. It's going to be the derivative of u in the direction of alpha prime of t, and then dot product it with alpha prime. Okay. My notes indicate that the book writes it this way. I think it does. Okay. So, but realize that the question is: are we thinking of things as a function of t, or are we thinking of things as defined on the surface? If it's defined on the surface, you're taking the derivative along the curve alpha prime of t. You think of it as a function of t, you're just taking ddt of both sides. But then this proves the theorem, right? Because this plug in t equal to 0, and this term is that term, and this term with the minus sign is that term, and they add to 0, so that proves the theorem. So done. I need to put it like that. Sure. Yeah. Okay. Now, why do we care about this lemma? Well, we can. It really motivates a new thing, which we can call normal curvature. And this normal curvature is defined to be, we're going to use a little k. This is not a capital K, it's a little k. Capital K was the Gauss curvature, remember that? That's a number at each point. This is a function of our unit vector u. Here, they're using u, so let me call this u here. That's a little u. Not to be confused with the capital U, which is the normal vector everywhere on the potato, right? Okay, this is what the book does. Okay, I'm just following them. Blame them, not me. Okay, little k of little u is defined to be, this is a definition, so I'll put 2 dots over it, to be this quantity here. Right. So the shape operator, you plug in u, dot product u. Okay. It's a definition. Now, by the way, it also would equals alpha double prime of t dot u, capital U, for any curve alpha of alpha, which has velocity vector u. Okay, so we have that identity. So it gives some meaning to what this means. Okay, what does k of u mean? Well, it is the normal curvature, right? It's because what is this alpha double prime? We think of that as the curvature vector, right? The length of that is what we used to call kappa for curves, right? And if we say, well, and we could call alpha double prime of t in general, we could call that the curvature vector, I suppose. It's the direction. I mean, it needs to be parametrized. Let's go ahead and parameterize it by, let's make it a unit speed curve. How about that? This would be the most interesting case, right? And the most interesting, so then u here would be a unit vector, right? In which case, this alpha double prime of t, which is really, I could think of it as like a beta double prime of s, right? Because it parameterizes my arc length. That thing is like a curvature vector. And then I can just say, well, how much is it curving in the direction of u? Right. So in other words, if I have an ant walking on a potato, I don't care if they're curving left and right. I'm wondering how much of the curvature of the ant is because of the potato. You guys get the idea? How much are they curving in the directions that he has no choice about, which is the directions perpendicular to the surface? Okay. And so that's why it's called normal curvature. There's a better name than normal curvature, although normal curvature is not bad. I like to call it cross-sectional curvature. So I'll humor them and call it normal curvature, but it's also, because I understand why they call it normal curvature, because of this limit here, right? It's alpha double prime dot u. Okay, normal curvature. But in terms of the picture, what does it represent? It represents cross-sectional curvature. And the reason is because of this proposition here. Is that, let me draw this potato again, I guess. Is that if I take this U here, right? I suppose it's in the chalkboard there, and I have the capital U going here. They're both unit. Little u, capital U. Make this bigger just to emphasize that. You have a potato that's coming out of the chalkboard, right? But can you all see that the chalkboard is also giving us a cross section of the potato, right? So there's a plane defined by capital U and little u. Right? The tangent plane is still there. Let me not draw it. It clutters the picture. But imagine the plane defined by u and capital U. That's going to cut your potato, sort of slice it, right? And then what I have is in this plane here, in the plane defined by u and little u, this plane right here, right? It gives me a cross section. I actually get a curve here, right? It goes all the way around for that matter, right? But I get this cross section, and in particular, I get a curve here. And it turns out the curvature of this curve, so here's the, they call it proposition 243 here. And that is that the normal curvature of u, of little u there, is equal to, up to a sign, it's the curvature of this curve here. This cross section here, this curve here, we'll call it sigma of S. Okay? And let's say this point right here is our usual P, which we'll call sigma of 0. Follow the book. And so this is the curvature of this curve sigma at 0, right? So at the point P there. So whatever this curvature is right here, that's telling you what the normal curvature is up to a sign. So it's really cross-sectional curvature. And how do we prove it? Well, it actually just follows directly from the lemma there. So you see the cross-section. Now take this curve, parameterize it by unit speed. Fair enough, right? And so we know that so then the proof is we'll just define sigma is the unit speed curve, unit speed parameterization, right? Curve in the cross section. And so what does that mean? We mean sigma of 0 is equal to the point P. Sigma prime of 0 is equal to that u, right? And then when you parameterize the arc length, we know that sigma double prime of 0 here, of course, it's going to be in this plane. And not only that, it equals plus. It's going to be plus or minus kappa times u, isn't it? Right? Because we know the length of this is what we normally call the curvature, kappa. Right? And so, and we know it's going to be in the plane and it's perpendicular to u, so therefore it's either going in the direction of u, capital U, or the opposite direction, so it's going to be plus or minus kappa u. And then you just plug into our theorem here, right? And you see that this theorem here is alpha double prime dot u. So, you take, in this case, sigma double prime, when you dot with u, you're going to get plus or minus kappa. And so that's how we prove the theorem. Okay. Yes?
Can you explain the figure again, the cross section?
Yeah. So I have a potato. And so here I've drawn the tangent plane. You see the capital U is fixed. But this little u, there's a whole circle of possible little u's, right? So pick one. Which one do I want to pick? Well, so I can draw the picture more easily, let's have u, think of this as a three-dimensional thing coming out of the chalkboard, right? U is in the plane of the chalkboard, okay? And then, given a little u and a capital U, that defines a plane going through the point P. What I've drawn here, this sigma as a graph is equal to the intersection of my surface, M, intersect the plane defined by capital U and little u. All right, that's a curve. right? And it's in that plane defined by capital U and little u. And then it turns out whatever the curvature of that curve is at the point P is what the normal curvature in the direction U is of that surface at that point. So this plane, this cross-sectional plane, is a circle of possible ones, right? And so what does this mean? What it means is that cross-sectional, I call it cross-sectional curvature. Normal curvature is also, could just as well be called cross-sectional curvature, because it's simply the curvature of the cross-section. The cross-section, each time I intersect with a plane, again, not just any plane, a plane that contains capital U, right? So it's given a surface, like if I have a beach ball, pick the North Pole because it's all the same anyway, right? You have a capital U is pointing straight up. I have these planes that all intersect the beach ball in great circles. And so I know what the normal curvature is. It's just the curvature of each of those circles, right? Each beach ball or a sphere intersect a plane is always going to be a circle. And not only that, and because these are planes that contain the normal vector, in the case of a sphere, it's going to be great circles. And so the radius of those circles will be the same as the radius of the sphere. And so then I know that up to a sign anyway, this tells me what the normal curvature is. Now why is it up to a sign? Well, this shape operator is really kind of two shape operators, because what is a shape operator? Shape operator is defined to be the rate of change of this u, right? But, well, which u do I use? The normal, because it's the one that points out or the one that points in, right? Or what if I have a surface that doesn't have an inside or an outside? What if I just have like the xy plane? I use the one that and what if it's at an angle, right? Who am I to say which way capital U has to point, right? So the shape operator in many ways is only defined up to a sign. Okay, it's the shape operator. Pick one, right? And then do your calculations with that. But you could if you switch the sign on U, just replace capital U by minus U, then the shape operator changes by a sign, which means the normal curvature would change by a sign. And so this is about as good as you can do. And this is where I things get really cool, by the way. We're trying to get some really cool insight, which I've referred to before. But last time we showed, remember last time, the shape operator is symmetric. And what does that mean? It means, in particular, if I choose an orthonormal basis, then the matrix representing the shape operator will be symmetric. Okay? The actual identity, right, is, okay, so first of all, V dot product shape operator of W equals W dot product shape operator V. Okay, but then two, this means that in an orthonormal basis, for the tangent plane, right? That means the matrix A will be symmetric. A, B, C, C, I think is the way the book did it, right? But then that implies real eigenvalues. There's a quadratic equation you get, since the quadratic equation you get is A minus lambda, B minus lambda minus C squared equals 0, right? That's the equation you're solving, and you can see that's always got two real roots. Why? Because without the minus C squared, this quadratic has two real roots, lambda equal to A and B, and then minus C squared drops the parabola down even further, right? So you definitely have two real roots. And then that means then the eigen. So there's two possibilities, by the way. If lambda 1 equals lambda 2, then this implies that your A equals just lambda 1. Well, this implies that your shape operator, let's say lambda 1 equals lambda 2, equals lambda, then this would imply that your shape operator just means multiplied by lambda. So that's case 1. Case 2, right, would be lambda 1 not equal to lambda 2. Then this implies that the eigenvectors are orthogonal. That's a classic linear algebra fact. Did I prove it last time?
Not the first one.
Okay. Did I prove this thing here last time? I'll just review it real quick. So what does that mean? It means that if I have two eigenvectors, let's say the shape operator of V1, or what do they use for eigenvectors? U1, U2, okay. So yeah, another little U. So let's say we have this situation, right? Right? Okay, so we have two eigenvectors, U1, U2, and lambda 1, lambda 2 are their eigenvalues. Okay? Then what you do is, this is a classic thing, you want to make sure you never forget this. But if I look at the quantity, I look at this quantity right here, okay? And plug in U1 and U2, right? Y'all see that?
Why?
I'm going to save some chalk here. Plug in U1 and U2. Then what you get is U1, okay, I'll write down shape operator of U2 is equal to U2 dot product shape operator of U1. And so this means I'm going to get shape operator of U2 means you get lambda 2, right, times U1 dot U2. This is lambda 1 times U1 dot product U2. Agreed? Everybody follow what happened so far?
No.
All right.
I lost at the U substitution step.
Okay, so this is something we proved last time, that the shape operator is symmetric.
Yes.
True for all vectors v and w.
Okay.
Let replace v with u1 and w with u2.
Sure.
That's why so I just recopied it with plugging in those vectors.
Yes.
But the shape operator of u2 is equal to lambda 2 u2. So what the lambda 2 factors out, I get u1 dot u2 here.
Okay.
Shape operator of u1, it has an eigenvector u1. And so this is equal to lambda 1 u1, so the lambda 1 factors out, and I get u2 dot u1, which is u1 dot u2, because dot product is symmetric.
Yes.
Okay. And now what you can do is we can set this equal to 0 by subtracting the raw off the right-hand side, and we get lambda 2 minus lambda 1 times u1 dot product u2 is equal to 0. Okay. Just collected terms. And the point is, we're saying lambda 1 is not equal to lambda 2, so I can divide by that. It's not 0, okay? So that means that u1 dot product u2 equals 0, which means that u1 is perpendicular to u2. So that's how you prove that for a symmetric operator, when you have distinct eigenvalues, the eigenvectors are perpendicular. Okay? That's a classic linear algebra fact. Okay. Very nice, right? And people will assume you know this for the rest of your life, so you should learn now, or other people are just going to be quoting it, right? I was very tempted to do that just now. Okay. And so what does this all mean? By the way, it means that since these are the two possible cases, right? The shape operator, therefore, so then here's my fifth thing, is that the shape operator may always be represented with a matrix A equaling to lambda 1, 0, 0, lambda 2. whether lambda 1 and lambda 2 are equal or not, right? Because remember, when lambda 1 equals, if they're not equal, then we know that I can choose a basis where this would be the representation matrix, right? But if they are equal, and this means the shape operator is multiplying by lambda, but this is multiplying by lambda, right? If lambda 1 and lambda 2 are equal. The only difference between these two cases is that here I have to choose my orthonormal basis to be the eigenvectors. And up here, every vector is an eigenvector, so just choose any orthonormal basis you want. Okay? So I can say, as that for some orthonormal basis. U1, U2. Okay, if they're the, and so U1, U2, and where U1, U2 in fact are eigenvectors. They must be the eigenvectors in the second case. In the first case, every vector is an eigenvector. Okay? So this is what I'm going to be assuming from now on, is that, because we had this whole problem, we defined this shape operator, and there's just some plane. And of course I drew this plane to be flat, but of course the plane is at an angle over here, and it's at an angle over there, right? And so you can't just say, there's no canonical x-axis or y-axis for your plane, right? Like, what's my canonical orthonormal basis for the plane? Well, now, I kind of sort of have one, right? I mean, the best choice is this case 2, and if lambda 1 is not equal to lambda 2, I just use the eigenvectors of the shape operator as my canonical basis, and then my A comes out really nice. It's a diagonal matrix, right? It's like all zeros except for along the diagonal.
So once you diagonalize the matrix and change the basis, then your eigenvectors in the new basis are just 1, 0, 0, 1.
We're represented by the numbers 1, 0, and 0, 1, yeah. Yeah, exactly. So everything is like, oh, okay, well that's nice, because it's kind of like the nicest possible thing, right? So now we have like a canonical basis vectors, the eigenvectors, right? And my matrix is just lambda 1, lambda 2. Okay, so why don't we do that, okay? And so in other words, now we can come back to this tangent plane. Oh, let's just go ahead and write it again. So there's my tangent plane, right? And now the point is there's two vectors, u1 and u2, that are our canonical basis, and these are the eigenvectors, right? And if I take any other, and let's go ahead and make them give them length 1. Okay, I don't know if I said that, but you know, eigenvectors, it doesn't matter what length you give them, right? Because if u1 is an eigenvector, if I multiply it by 5, right, it's still an eigenvector, right? It's a whole array of in fact, negative and positive array of vectors is also an eigenvector. So let's just choose it to have length 1. So u1, u2, let's just choose them to have length 1. And so now if I have any other unit vector, it's going to be of the form cosine theta u1 plus sine theta u2. That gives me all other possible unit vectors, doesn't it? Basic trigonometry. Do y'all remember the definition of sine and cosine?
Yeah.
Go ahead. There's a 50-50. The answer will be incomplete, by the way. So just realize that. What is the definition of sine and cosine? Anybody have the guts to say? Yes.
From what I remember, sine was perpendicular over height, and cosine would be so.
Yeah, that's what I was expecting most people to say, and that's great for angles between, like 0 and 90 degrees, right? Doesn't really tell you what the answer is for 540 degrees, right? Okay, so can anyone tell you what the definition of sine and cosine are for all angles?
Taylor expansion.
If you could take complex analysis and you want it to be defined for all complex numbers, then yeah, you have to do that. And so I'll give you points to that, all right? But maybe not quite so fancy, right? Yeah, I mean, because I want to get some geometric intuition. I just want it to work for real, all real numbers, yes.
The x and y coordinates on the unit circle.
There you go. All right, that's what I was looking for. So just and you guys know that, right? So the point is, if you have a circle, by the way, I made an artistic error there. I drew the circle last. Draw the circle first, right? Forgot. I'm a little excited about sine and cosine. The point is, I take out some point here, right? Take this angle here. That angle, we call it theta. then the point is that this is cosine theta, comma sine theta, where, by the way, this distance right here, the actual distance along the unit circle here, that distance is theta, and that's how you define sine and cosine in terms of radians, right? That's why we have 2 pi radians equals 360 degrees, right? In fact, so radians is really the natural measure, right? So really, sine, cosine, they simply parameterize the unit circle. Unit speed. Unit speed parameterization of the unit circle is the definition of sine and cosine. And you guys all know that. If the angle happens to be less than 90 degrees, then you can also see, right, that, this is 1, then the base here is cosine, the height is sine, right? And so if the hypotenuse is 1, then it's sine is the side opposite, and cosine is the side adjacent. More generally, it's the ratio with the hypotenuse, right? Yes?
So could you explain why that leads to any other vector u?
Yeah, because another way to write this point, right, sine comma cosine, is that this equals cosine theta times 1 comma 0 plus sine theta times 0 comma 1, right?
Sure.
And so what you can see now, 1, 0, and 0, 1 are like basis vectors, right? And so you call them I and J if you like, right? And so more generally, if you replace 1, 0, and 0, 1 with any perpendicular vectors, this parameterizes the circle in the plane defined by U1 and U2. So this is this is a unit circle in the U1 U2 plane. And now how do I know it is, well, compute the length of this, right? How do I compute length? I take this vector dot product itself, and if I want the length to be 1, I better make sure that u dot u equals 1 squared, right? All right, so go ahead and take this dot product itself, and what you're going to get is u1 dot u2 is 0. That's, remember, perpendicular, right? These are orthogonal. We do need that. We do need that. And so if I take this dot product itself, I'm going to get a cosine squared u1 dot u1 plus sine squared u2 dot u2. u1 dot u1 is 1, u2 dot u2 is 1 also, so I get cosine squared plus sine squared, which equals 1. So this vector has length 1. For the same reason that this one vector does. All right, so that's your general. So now we have a nice general formula for a vector in the tangent plane. So now let's understand normal curvature then, or cross-sectional curvature if you like. Normal curvature then, we have k of u, plug in this u. Well, by definition, it's cosine theta u. Well, I feel like I'm skipping the definition. Let's put the definition in. So normal curvature, it's right here, right? So it's u. All right, this way. U dot product, the shape operator of u. By definition, what is u? It's cosine theta u1 plus sine theta u2. And then dot product the shape operator applied to u. But the shape operator is linear. So when I take the, okay, I'll go ahead and put this in. I can tell I'm fighting the urge to skip steps.
Thank you.
It's subconscious is the problem, okay? So I just made a substitution. Now we do the shape operator of u1, we know what you get. Shape operator of u1 is lambda 1 u1. So I get cosine theta times lambda 1 u1 plus sine theta times, this is times, not dot product, lambda 2 u2. Agreed? Anyone have any questions about this? Here's just the definition of eigenvalues there. And now keep in mind that u1 dot u2 is 0 and u2 dot u1 is 0. So whereas I normally have 2 terms here and 2 terms there, you do the distributive law, you expect to get 4 terms, right? 2 of the terms are 0. And so the only terms that aren't 0 is the dot product of the first two and the dot product of the last two. Now, can anyone tell me what u1.u1 is? It's 1, because it's a unit vector. Can anyone tell me what u2.u2 is? 1, right. So this first term then is just going to be lambda 1 times cosine squared theta, right? Times 1, because u1.u1 is 1. And the second term is going to be lambda 2 times sine squared theta. Oh, it's a nice formula. And then furthermore, we have an identity. The identity is that cosine squared theta plus sine squared theta equals 1, right? That's our sort of the first and main trigonometric identity, right? I'm going to say it's the first one. Okay, if I make that substitution, then I can replace sine theta by 1 minus cosine squared theta, right? And if I do that, then I get, by the way, there's another convention that we're going to do. And that is, I learned this from a professor at MIT, but you don't have to be an MIT professor to do this. Do you guys agree that lambda 2 should always be bigger than lambda 1, bigger than or equal, right? Like, obviously, right? Because 2 is bigger than 1. Like, if you're trying to figure out how to number things, oh, gee, what should I do? Which one should I make bigger, right? Well, 2 is bigger than 1, right? So, like, it's funny. A lot of professional mathematicians don't respect this convention. They'll just arbitrarily, oh, let's call this one this and call that one that. And the next thing you know, their lambda 2 is smaller than their lambda 1, or their A2 is smaller than their A1. So anyway, I think this is a good convention to respect, I think. And so let's go ahead and have lambda 2 be the bigger of the two numbers. But they might be the same. Then if I substitute away for the sine squared, I get lambda 2, and then minus lambda 2 minus lambda 1 times cosine squared. Okay. Did I do the keep? You know, I got some minus signs. You got to keep track of there. A minus times a minus is a plus, right? And then there's another thing I could do. Let's substitute away the cosine squared. Cosine squared is 1 minus sine squared. Then I'll get lambda 1 plus lambda 2 minus lambda 1 times sine squared theta. Did I do it right? Okay. Now, pop quiz. What's the smallest possible value of this bottom expression here? What's the smallest possible value? What should I let theta be to minimize this quantity? 0, right? Because I can't make sine squared less than 0. That's something squared, right? So theta equals 0. And so lambda 1 we see is the minimum possible value of sectional curvature. But then if you look at the equation above, hey, pop quiz, what's the largest I could make this possible value? Well, you're subtracting something here because lambda 2 is greater than or equal to lambda 1, right? And so you want to make this 0, so you let cosine theta be 0, means theta is 90 degrees. Or 270, whatever. Right? Up to a multiple of 180. And so then lambda 2 is the maximum possible value. So not only do we have these formulas here, but we have a theorem, and that is lambda 1 is equal to the minimum k of u, where you take you know, of all possible u that have length equal to 1, right? And lambda 2 is equal to the maximum value of normal curvature, where length u equals 1. Okay, and now, boy, we're getting some insight, aren't we? We're getting some insight.
Oh yeah.
And so in other words, cross-sectional curvature / normal curvature, it's a function, but it's not a complicated function. It's always a function of this form here. And by the way, all three ways are equally nice to understand it, right? K of u equals this, right? I mean, which formula do you want to use? Well, it just kind of depends, right? But it's sort of an interpolation between lambda 1 and lambda 2. Lambda 1 being the smallest possible value, lambda 2 being the maximum possible value. And then you got everything in the middle. So really you only need to know two numbers. K of u is not just some arbitrary thing, right? Once you know lambda 1, lambda 2, you got the whole formula. And so really it's a sine wave. Are you all familiar with the fact that when you take sine waves and cosine waves, you square them, you still get sine waves. Right? There's half angle formulas, right, that you can use. And so in other words, as a function, k of u just oscillates. And by the way, its period is 180 degrees, not 360, because when you square it, it decreases the period with the half angle formulas. Right? And so I guess if we want to go ahead and graph it explicitly here, the point is when you get a minimum value when theta equals 0, right? And maximum value when you get to 180. So let's see here if I can draw a sine wave. So at 90 degrees it's maximized, right? At 0 degrees it's minimized, and then at 180 degrees it's minimized again, so on. And so this is what your sectional curvature looks like. I guess that you could keep on going, right? You guys get the idea. The period, though, is 180 degrees, not 360 degrees. And by the way, your principal curvature directions are directions up to 180 degrees. So in other words, which by the way makes sense. Let's go back to the cylinder. Remember, take a point on the cylinder. You've got this tangent plane, and one of the directions is along the circle, and one is along the spine. Right. Now, which way around this? Do I go this way along the circle or that way around the circle? Your choice. Who cares? Nobody cares. Okay, it doesn't matter. Same thing, right? You're picking a direction, a sort of unsigned direction, right? You're picking the line defined by the direction. So you have two perpendicular sort of lines, right, that are sort of form the x and y axes, but sort of unsigned x and y axes. All right, so just arbitrarily define U1 to be coming out of the border, in the border, nobody cares, right? U1, and then U2, is it up or is it down? Who cares? Well, I'll have it up here in this case, but it doesn't matter. You can have it going down if you want. And so if you can just figure out what so in other words, what is let's say this has radius capital R here. Now we have to decide which way capital U is going. Let's go ahead and have capital U pointing out. I tend to like capital U to point out when there's an inside. I don't know, but sometimes, pointing in, whatever. I don't have a strong opinion on this. And so then what is the shape operator here? Well, all I really need to know is K1, K2. I already know U1, U2. I mean, okay, I'm using the argument. Any fool can see that argument. Are y'all familiar with that argument? You ever use it in your homework? Obviously, and then you write something, right? So, by the way, which is how you find errors in mathematical papers. If you ever want to like find an error in someone's work, just do a search on where they say obviously, right? That's the thing they didn't check, right? Yeah. So, any fool can see that, right? That if I look at cross-sectional curvature, it's maximized at the circle, right? And it's minimized along the spine, right? That happens to be true in this case, but obviously that would require proof, right? Okay, I'm not saying, but okay, let's just start with our intuition, right? And so then you can say, oh, okay, now is the curvature positive or negative here? Well, I have U pointing out, right? And so actually, if I look at the cross-sectional curvature, right? I mean, if I look, or let's look at the definition of the shape operator. Where is it? Right here, right there, right? Okay. So that we have to look at that minus sign there, right? And so there's two ways we could do this. I think maybe it's easier to use the fact that this identity right here, right? Maybe it's easier to do that. And we can see that I know that the curvature vector is pointing in, right? You guys see that because I'm curving this way. The curvature vector is pointing in. We may recall that. And so that's pointing in, that's pointing out. So actually, what I have is I have K1 and K2. One is 0 and the other one is negative. So 0 is actually the larger of the two. And this K2, whoops. Okay, so this the smaller is this K1, which is negative 1 over R, right? Because we know the curvature of a circle radius R is 1 over R, right? The alpha double prime is pointing in, it's opposite of U, right? So this dot product is going to be negative 1. Or it's going to be negative. Okay, so K1 by convention is smaller than K2. So those are my K1 and K2. I know what my two eigenvectors are. They're as drawn. And there you go. Now what's kind of cool here then is this gives you a little more of a geometric notion of what Gauss curvature is and what mean curvature is. Because once I realized that lambda 1 and lambda 2 are the max and mins of the sectional curvature, you all recall that your Gauss curvature, capital K, that's lambda 1 times lambda 2. Why? Because Gauss curvature is the determinant of that shape operator. But the shape operator has a representation with pure diagonal, right? The determinant is just lambda 1 times lambda 2. So the Gauss curvature is the product of the maximal and minimal sectional curvatures. Now that's intrinsic geometry, and you might say, well, wait a second. I thought you told me that the shape operator is only defined up to a sign, and does that mean the Gauss curvature is only defined up to a sign? Well, it's actually kind of a cool answer. Shape operator is defined up to a sign. That means lambda 1 and lambda 2 are defined up to a sign. In other words, had I had u pointing in here, I said K1 and K2. I think we're using lambda 1 and lambda 2 here, right? I don't really care. Does the book use lambda 1, lambda 2, or K1 and K2? At some point, it seems like we go to K1 and K2. Yeah, I think we do. Okay, so you guys might, I'm going to start using K1 and K2 now, okay? Or instead of lambda 1 and lambda 2. They're the same thing. So the point is that, well, I guess I did over here anyway. So I'll just point out that the same, lambda 2. When you're talking about eigenvalues of the shape operator, we call them K1 and K2. Because they're actually represent something. They're not just eigenvalues. They are the max and mins of the normal curvature.
Why is there another K?
Yet another K, right? So K1 and K2 are little K1, little K2 are the eigenvalues of the shape operator. Little k with no index, that's the normal curvature. It's a function on unit vector, unit tangent vectors. And of course, capital K is the Gauss curvature, which equals lambda 1 times lambda 2, or K1 times K2. And then twice the mean curvature. This is the trace of this, right? That's lambda 1 plus lambda 2. And now you see why they used 2h equal that. Mean curvature is the average of K1 and K2, or lambda 1 and lambda 2, right? That's why it's the mean curvature. It's the average value of the normal curvature. Does that make sense? Okay. And then at some point, people realize that, you know what, traces are way more natural than averages. So taking the trace, and so at some point, it really should have been called the trace curvature instead of the mean curvature. Too late now. So here's what's crazy. People still call it the mean curvature, but they drop the 2. So in any outside this class, that 2 will not be there. They just take the trace and call it the mean curvature. Doesn't make any sense, does it? Okay. There's no one in charge. This is the problem. There is no one in charge of. It's just sort of like textbooks get written. Okay, well, everyone else is doing it this way, so we'll have to follow the convention, right? And every once in a while, someone has the nerve to say, I'm not following that convention, it's just too stupid, right? And things improve. But then people get mad because, oh, I thought you meant this, right? So it's, maybe eventually things will get straightened out. It doesn't really matter, it's just a factor of 2. So now we have a really beautiful picture here, don't we? This has been a beautiful lecture so far, hasn't it? Okay.
Just to make sure I'm keeping things straight.
Yes.
In proposition 243, what's the kappa on the right hand side of the equation? Kappa or the subsigma? Yeah.
Here? Yep.
Yeah.
Your kappa, yep.
Okay. And that's what?
Oh, this is the curvature of this curve sigma in the cross section.
In the cross section.
It's the curvature. So it's chapter 1 stuff, right?
Right.
It's that kappa curvature, right, of a curve in a plane.
Okay.
Yeah. Other questions? Here, let me tell you what I like about this lecture. Starts out beautiful, ends ugly. All right, so you guys taking the beauty. All right, so what a beautiful picture this is, right? Now let's get some formulas, right? Which, by the way, is ultimately necessary. If someone says, here's my surface, I have a following parameterization for a surface. Now, give me some formulas, right? Okay, let's see if we can get this done. Let's compute. Let me show you how to actually compute stuff. Well, I have to erase the board. So, any questions before I erase this very nice, beautiful picture? Right? Can y'all internalize it? Okay. And then we proved it. So that make sure it's in the book, right? Master this. Okay. I will test this on tests and stuff. me to erase this. I love this board. I'll tell you one of my favorite stories. I taught in this classroom, and then right afterwards there was a faculty meeting, which quite often happens at noon, so it could even happen for this class some one of these times. But we have them like once a month or so. And I had just explained what special relativity was. I had just written on the board that special relativity was a minus sign in the rule of Pythagoras. And I'd written in nice big letters, and I had some pretty pictures. And when I walked in, I was a little bit late, and everyone else was mostly already there. The meeting hadn't started yet. And I walked in, and I overheard one professor explain to another professor that, yeah, special relativity is just a minus sign in the rule of Pythagoras. Just from my board work, right? And like I saw learning happening, right, among the faculty, right? And I was like, oh, this is awesome, right? Like, yeah, special relativity is just a minus sign in the rule of Pythagoras. And like, I was just so pleased that someone had not realized how simple it was, right? But now they did. Okay, some formulas. What we're going to do is just pick any two vectors, v and w, okay? They don't have to be perpendicular. They're not perpendicular in this picture, even if they might look almost perpendicular. All right, this is the tangent plane at T. There's your point P. This is your surface M. Let's suppose that so v and w is any basis, okay? It's nothing special. It's any basis for the tangent plane at the point P, okay? And let's suppose the shape operator of v and the shape operator of w, well, we need to express them in terms of the basis to get a representation matrix. And so let's say we get these coefficients, okay? You guys see the idea? V and w are vectors. So shape operator v at the point P, this is going to be some vector. You guys want to put the vector symbols in there, just to remind you? And so since v and w, they're literally independent. That's the only thing we're assuming. We can, whatever that is, it's some linear combination of v and w. And so what this does is it gives us our representation matrix A, and it equals A, B, C, D. That's our representation matrix for the shape operator. Fair enough? Now, we already know what K is. The Gauss curvature is just the determinant of A, which, by the way, is AD minus BC, right? And you might be like, really? I thought we had to use special A. No. That's what we learned last lecture, right? Any basis works, right? The determinant is invariant. Choose any basis vectors you want, and you'll get the same determinant. You also get the same trace. The determinant and trace are invariant on your choice of bases. So 2H, this was the trace of A, and so this was going to equal A plus D. Okay? So if you want to compute K and H, you can just pick any basis vectors you want, compute this, figure out what A, B, C, and D are, and plug into those formulas. And sure enough, that's one way to compute K and H. Well, let's go further. Another way to get a formula is this identity here. I'll call it identity 1. You look at S of V cross product S of W. And so this is equal to A V plus V W cross product CV plus DW. And now I am going to skip a step here. It's in the book, okay? Don't take notes. Try to understand. Can anyone tell me what W cross W is?
0.
0. Any vector dot product. Any vector cross product itself. I said A W dot. I meant cross product. We're using a distributive law. We should get 4 terms. But W cross W is 0 because any vector cross product itself is 0, right? The parallelogram, they span a 0 area, right? So it's going to be the 0 vector. Anyone tell me what V cross V is? Also 0. So the only 2 terms we're going to get are this cross that and that cross that, right? One of them is V cross W, and one of them is W cross V. but W cross V is negative V cross W. Y'all remember that? With cross product, when you switch the vectors, it changes by a sign. So I just introduced as a minus sign. So therefore, what I'm going to get then is AD V cross W, and then I have a BC W cross V, which is negative BC V cross W. And hey, look, the determinant showed up. Isn't that nice? So another thing you could do is just choose V and W. I don't care what they are, right? Compute, as long as they're linearly independent. Compute S of V, compute S of W, take their cross product. Look at V cross W. What you'll find is that these vectors are parallel, and the factor between them is, in fact, a determinant. Okay, that's pretty cool. And by the way, there's a second trick you do to get mean curvature, which is the shape operator of V cross product W, and then plus V cross product shape operator of W. This equals similar trick, and what you're going to get is A plus V cross W. Y'all see why? I left out a step there, but S of V equals that. Your cross product with W, W cross W is 0, so you just get the A V cross W. And the second term gives you D V cross W. Just set up to work out. And so there you go. There's your mean curvature, right? Okay, so this equals 2H V cross W. And this right here, by the way, okay, I'll go ahead and finish it. This equals K V cross W. All right. And then we get to the Lagrange identity. Y'all know who Lagrange is?
He's big in econ.
One of the top 10 mathematicians of all time. Something like that. French guy.
Wasn't he like half Italian?
Oh, no. Lagrange is awesome. No. I will not have Lagrange.
I could be wrong.
No.
He was
He was talking about where he's from.
Oh, whether
Oh
he's
yeah,
French
yeah,
or
yeah.
not.
I think I had an Italian professor who was like very adamant that he was actually Italian.
Oh, okay. I thought you were saying he wasn't top 10.
Oh no. He's
Okay, no, I was like taking offense at that. I have no idea. I just assumed he was French, but you tell me. I know
Oh,
that
yeah.
France claims him, right? But
Yeah. See, so he was born in Italy, and then later he decided that he was French, and then so now like all of like French math like claims him.
oh, interesting. Okay,
Yeah, but it's contentious.
I see. Now, was he of French ancestry before he was born in Italy, or was he just an Italian who decided he preferred to be French?
I can check.
I'm certainly curious to know that.
Which year, approximately?
He's of Italian and French descent. He was born in Turin, in northern Italy.
Okay. Okay, I did not know that.
Okay, yeah, sorry.
I'm going to tell you a funny story about involving Lagrange, actually. My grandfather was a mathematician. It's probably why I'm a mathematician. You know, I thought it seemed like a very normal profession to me. Like, my dad's dad was a mathematician. Okay, I'll be a mathematician. And my grandfather died when I was 8, unfortunately, so I never got to know him. He had no idea I ended up being a mathematician, right? I'm named after him. His name was Hubert Bray. My dad was Hubert Bray Jr., and then I was named after my grandfather, the first mathematician. So we all have different middle names. So I'm the third Hubert Bray in a row. So the first Hubert Bray, apparently, was not only a mathematician, but he collected rare math books because he appreciated them, right? It's like, oh my God. So he was in France one time, and he saw a copy of Lagrange's Mécanique Analytique, his masterpiece. And somehow or another, he got a copy of it. Now, it's interesting to guess how he got a copy of it, because this is a masterpiece, okay? But when my grandfather died, his copy of Lagrange's Mécanique Analytique was on his bookshelf. Okay? Now, here's the tragic thing about it. Nobody knew. Like, he died. I don't know, did he not tell anyone? By the way, after I die, there's this, in my mind, almost priceless book on my bookshelf. Or maybe he didn't think of it as priceless. I think it was something significant. Now, can you even buy something like that? I know he was in France at one point. Maybe he just bought it. Maybe he found it. He was in a rare bookstore or something like that, and saw, or in an old bookstore and saw it. It was like, did they realize what they have here, and bought it for $5? I have no idea. Okay, that story is lost. However, I do know that there was a French mathematician, Mandelbrot, Shlomo Mandelbrot, who, by the way, was the uncle of Mandelbrot set fame. And he was best friends with my grandfather. And it was the 1930s, and Mandelbrot was Jewish. And he contacted my grandfather and said, hey, it's getting a little tense around here. Do you think I could come to Rice University, where my grandfather was a mathematician, me and my family, and we could be mathematicians where it's a little bit safer, right? And so my grandfather arranged that, and so Shlomo Mandelbrot came to Rice University, where my grandfather was professor. Can only imagine he might have taken what he thought were the most valuable possessions, right? And so it's possible, I'm just speculating, he might have taken some of the most important math books that he had access to, and he was one of the top professors in France, and so you can easily imagine he might have taken this book with him. And I also can easily imagine he might have given the book to my grandfather as a token of his appreciation. I could imagine that, right? This is me making stuff up, but it's certainly possible, right? But anyway, when my grandfather died, this amazing book is just sitting on his bookshelf, and it stayed there. That was 1978 until 1987, when my grandmother finally died at the age of 90. And then my mom and I and my brother, we were over at my, grandmother's house. She had just died, and she said, hey, there's all your grandfather's books. Maybe you might want to take one or two just to, something to remember your grandfather by, right? I was not interested. But my brother said, well, okay. And so he just went through the whole bookcase, and he found, I think, like 5 of the oldest books, and he grabbed the 5 oldest books off the shelf and walked off with them. One of them was Lagrange's Mécanique Analytique. He's just a teenager. He has no idea what he has in his hands. Okay? And he is, and then it turns out like 3 of the books are, I think all the books were basically worthless except for that one, which is practically priceless, right? And so he just, when he's a grad student in mathematics, at some point he realized it was a more important book, but he still didn't really register on. And he had it sitting on one of his tables just for decoration. And I think later he became an instructor. He's a professor here now at Duke. You may recognize him, Clark Bray. But at some point he had this book sitting on his desk, and he was an instructor at Santa Clara University, and one of his professor friends came over, and that professor friend was a rare book collector. And he just walks in the room and just glances at the book, right? And doesn't even have to open the book or anything. Like, you can't even tell. He just recognizes the book, right? And he's like, I see you have a copy of Mécanique Analytique. And this is where calculus of variations is defined for the first time, right? Which is one of my favorite subjects to learn, that calculus of variations. Like physics, all of physics is based on it these days. The idea of an action. And Clark was like, how do you know the name of the book? Just by glancing at it, right? Because you could. And long story short, I think at the time back then it was like worth like $15,000, like on the black market. But of course it's like, should you even be able to own it, right? And so we ended up donating it back to Rice University. So now it's in the library at Rice University. But it's that's my interesting story with Mécanique Analytique and Lagrange. Okay, but anyway, here's Lagrange's identity. So. But yeah, learn calculus of variations. It's very super cool stuff. Okay, this is dot products on the right and it's cross products on the left. And I don't have a good intuition for this. There probably is. You can compute both sides and see it's true. Just let V equal V1, V2, V3, and W equal W1, W2, and just plug it in and see if both sides are equal. That will work. And other than that, maybe there's a nice geometric way of understanding it too. It's certainly possible. But here's the bottom line. The bottom line, though, take identity 1 and take identity 2. What we want is an actual formula for K. All right? And so what you find then is that K is equal to, what we're going to do is dot product both sides with V cross W, okay? Now, if you dot product V cross W, dot product V cross W, I can plug into this identity. Just let A and B be V and W, right? And so what we're going to get is we're going to get some mess of an expression over here. And now this is a vector dot product of vector, right? And then we're going to dot product with V cross W, so it's also this form. So we'll get a mess of an expression there. But the key point is, we'll be able to solve for this k here, right? And so this k then equals, when you plug in Lagrange's identity twice, it's S of v dot v times S of w dot w minus S of v dot w, S of w dot v, divided by v dot v, w dot w, minus v dot w squared. But I'll just write it this way, it's easier for you to check it. Okay? And then h, I'll write it as 2h. 2h is equal to S of v dot v, w dot w. Oh my God. Okay. Minus S of v dot w, w dot v, plus v dot v. I'm just copying this. I'm not figuring this out, right? It's in the book. Remember I said this was about to get messy? And it is v dot w squared, but I'm writing it this way just for easier to check it when you plug into the Lagrange's idea. Okay? All right, there you go. Now, what's the whole point of this? Suppose you have a coordinate patch. Y'all remember what a coordinate patch is, right? It's with the whole u and v, like latitude and longitude, gets mapped to your surface, right? Okay. And this is x of uv. And remember, like if this point here, maybe it gets mapped to this point here, and then whatever, we get an xu, that's one direction, then we get xv, that's another direction, right? And they're not necessarily perpendicular, it's just coordinates, right? And then there's some conventions we do. And we say, you know what? When you start computing things, you'll notice that the term xu dot xu comes up a lot, right? That's the length of xu squared, right? So it comes up a lot, so let's call that e from now on. And then xu dot xv, which by the way would be 0 if they're perpendicular, right? But more generally it doesn't have to be. That's what we'll call f. And then g, we'll call xv dot xv, okay? These terms come up a lot. By the way, we'll be using e, f, and g for the rest of the class. Turns out if you know those numbers, then you can take the dot product of any two vectors in a coordinate chart, right? Because all vectors are linear combinations of xu and xv. So I just need to know what the dot products of xu and xv are, and then I can use that in some plus some algebra to figure everything else out. And then there's also these quantities called L, M, and N. Okay, and what this is if I take the shape operator and plug in xu, and then dot product it with xu, that will be called L. And then the shape operator of xu, and then dot product it with xv, that will be called M. Okay? And then the shape operator, basically every possible combination, right? We'll do xv and dot product with xv, that will be called N. Now you might be saying, well, where is the shape operator of xv dot xu? Well, remember that equals, by symmetry, right? That equals M also, right? Okay, remember because shape operator is symmetric, you can switch these two guys. Okay, proved that last time. Okay, so with these conventions, turns out we can plug into these formulas and we get K is equal to Ln, that's just what that is up there, minus M squared, divided by Eg minus F squared. Doesn't that look nicer? It's a way to make that formula look nicer. See, it's just Ln minus M squared over Eg minus F squared. Right? Oh, that's not even so bad, is it? And what is H? Well, 2H still looks pretty ugly, actually. It's, what is this? GL plus En minus 2FM divided by Eg minus F squared. By the way, this EG minus F squared comes up a couple of times. That's the determinant of a matrix you may recognize. That matrix being sort of E, F along the diagonal and G's on the off diagonal. So I'll just point that out. And so is this Ln minus M squared if we think of this as a matrix as well. Now you might say, wait a second, how do I compute EF and G? Well, I have an idea. Given a coordinate patch defines a surface, just compute xu and xv and just compute it, right? That's easy. But how do I compute this stuff? It's kind of annoying right now, isn't it, right? But actually, from the theorem we erased today, term 235, we have formulas for L, M, and N that are convenient, which is that L is equal to U dot product X UU. Remember that L here is just normal curvature. Actually, this was the theorem I'm thinking of is from when we proved this, the symmetry of the shape operator. And so what we, you may recall that the shape operator of XU dot product XV, for example, whoops. Y'all recall that this was equal to U dot product XUV. Y'all remember that? That's how we proved the shape operator was symmetric, right? Because this is clearly symmetric in U and V, and so that will be symmetric in U and V. Okay. So we proved that identity last time. Was it last time? I believe it was last time. And so using that identity, when U and V are equal, right? You can see L here, right, is just going to be equal to that. M is equal to U dot XUV. And then N is equal to, I don't know, I should have done it this way. Better presentation, right? Okay. Now, so that, and these formulas, so when you're homework, if you have to compute stuff, use these formulas, right? So it's not even that hard, right? What do? You got your XUV, it defines the surface. Okay. Just some stupid coordinate chart. It might be really stupid, right? All you need is that XU and XV are literally independent at each point. So just not completely stupid. All right? And then you just plug in. And can you compute XU and XV? Sure. Can you take their dot product? Sure. Now you got EF and G. Can you compute the second derivative? Sure. Can you dot product it with U? How did you compute U? You took XU and XV, took a cross product, normalized it to have length 1, right? And then you take the dot product, boom, you got L, M, and N. Now you compute K, and now you have H. Now we have formulas for computing stuff. And here's what we have to look forward to next time. This is Einstein's insight, okay? Not Einstein, Gauss. Einstein wishes he was as smart as Gauss. Okay, I just flattered Einstein there. Okay. Actually, they're both pretty smart. Let's just say Gauss was better at math and Einstein was better at physics. So here's why. This might be Gauss's. This is one of his top favorite ideas ever. He realized that there's a formula for K, and it depends on the second fundamental form. But there's also a formula for K, and it only depends on EF and G. There's some identities he figured out, and it's a bit of a complicated formula. It doesn't really matter what the formula is, but here I'll write it. The formula is actually a little bit more complicated than this, but if you suppose f is 0, then the formula simplifies to what I'm writing down here. Okay, so this is actually the abridged version of it. But there's a version where f is not equal to 0. This so when f equals 0, the formula simplifies to this. Okay, but more generally, it's more complicated than that. And so that tells you that you can compute k just in terms of the EF and G's. Now, why is this important? The formula itself, who cares? Whatever. I don't have that memorized. But what I do have memorized is that K doesn't depend on L, M, and N, how things curve in space. It only curves on the EF and G's. Why is this important? Because the ant can compute EF and G. The ant understands latitude and longitude. I mean, do you guys, when you think of the Earth, do you think about the third dimension and outer space and all? No. You think of what's the latitude and longitude, right? you could think of I could go west, I could go north, south, east. What's the length of this? What's the dot product? What's the angle? Blah blah. You understand E, F, and G. This is actually something that makes perfect sense to the ant. Very natural, very normal. And so the ant can plug into this formula and compute K. K is a geometric invariant. It's intrinsic geometry. It does not depend on the three-dimensional space at all. E, F, and G are intrinsic quantities. L, M, and N are not. K, which we think of as the determinant, we think of as defined to determine the shape operator, and so it should therefore depend on the whole shape operator. Yeah, it's true, that's an identity, but it also can be computed just in terms of E, F, and G. And that's what we'll do next time. And that's what Gauss called his remarkable pair. Yes?
In terms of these formulas, we only need them if we don't have this matrix A. It's a lot easier to just...
Yeah, if you have the matrix A, you just take the determinant. But the problem is, it's just, so it's just a bunch of different ways to do the whole thing.
Is it less likely that we'll have the matrix A?
Yeah, it turns out this is the easy way.
Okay.
It's just sort of, you can turn your brain off here. You just memorize these formulas, you write them down, compute your E, F, and G, your L, M, and N, you plug into this, you just get the answer every single time. No cleverness required. Comment on that? Sometimes just doing it the way it doesn't require cleverness is nice, and sometimes you want to be